Hello everyone, and welcome to our series on electromagnetism. One of the important concepts you're going to learn is about electric fields. So, let's start with a small example. Say we have a wire, and we connect it to the positive terminal of a battery. Now, this battery is going to start trying to take out the electrons. So, we're going to get a positive charge along the wire. And anything that is charged has an electric field. What is an electric field? Well, basically what that means is this is charged. Let's take a charged particle. There's going to be a repelling force between the two. What's it going to be? Well, we think probably the force will get smaller the farther you go away from the wire. But that's just a guess. Let's find out. What would the electric field actually be? So in order to do that, first we're going to take a surface, and we'll say that it's pretty far from the ends. And we'll say that, just for this example, let's say we can count all of the electrons within this surface, and we can determine the charge Q inside. It also has a length and a radius. Now, before we move on, I'm going to have to take you back a little bit to subject of multivariable calculus, and if you remember, we learned something about the divergence theorem. And the divergence theorem basically says that all of the flow of anything going through this surface, for us, we just need this surface here, this is the total flow through the surface, is equal to the divergence throughout the volume. And in electromagnetism we have something really similar called Gauss's law, and what that says is that the electric field throughout the surface is going to be equal to the total charge inside divided by a constant. And so I said that this surface here is the one that matters because since we're so far from the edges, we know that our field is going to be the same all the way along the wire, which means that there's not going to be anything moving this way or this way, it's just going to be away from the wire. So that means we just have to integrate over this surface, and so if we know that it's not going to change, then the integral is simply multiplied by the surface area. This is the surface area of that cylinder, and this is going to be the total charge on the inside. If we just were to rearrange this, this is what we get. And we find, just as we predicted, that the farther the radius is from the wire, the lower the attraction or the force apart is. And we also find that the higher your charge per unit length on the wire, that is, the fewer electrons you have in any given part of the wire, the lower the force is also going to be.